Hi, my name is Stephen Richards, ID 100458273,
Hi, my name is Jake Jandu, ID 100584564.
and this is our Challenge 1 tutorial thing. Um, so basically, in our code, we use a deferred rendering system. So in a deferred rendering system, we have to have a geometry path, a lighting path, and the compilation, and then we can add any post-processing effects to the render scene afterwards. So to actually do a deferred rendering system, we need to actually create frame buffers. So first we create a geometry frame buffer by actually, if you look at the code, binding different position, normal, albedo, and we use a specular map in our code. So we have 4 different color textures for our actual frame buffer. We then, in our actual main loop, we send our texture values that we actually want to our actual shaders that we're going to use before we actually start rendering. And then we start our geometry path. So in the geometry path, we, as you see below, we render all the geometry we're actually going to have added to the scene. So if I run this, you will see that our geometry in our scene is our game. So we have word scenario odd, and in this we have our objects. So that's all the geometry we actually render. So in the geometry path, it takes all the geometry, gets the position values, the normal values, the albedo values, which is basically your color, and as well as your specular values, because we use a specular map, which is the shininess of the object. This all gets passed to the lighting path, which you can see here. This is where we take light volumes to calculate where on the scene we actually want to see our objects, so we don't actually render objects that are not actually visible. So in our case, we use spheres as our light volumes to actually cut off where we're not seeing our objects. We have 4 lights in the scene, which have a huge attenuation at the moment. So basically the entire scene is lit up. And then once we're done that, we actually pass it to any forward rendering that we want to do. And so basically that's our rendering system. And it follows the basic OpenGL pipeline, which is you pass your vertex shader to your either geometry shader if you require one. So for example, if you're doing particles, to your fragment shader, which does all your coloring and any post-processing effects, and then it adds it to your actual not rasterization. It's I believe, what's after? Well, it does any stencil or depth testing after that, and then it displays it onto the scene. Okay, so you want to talk about our lighting?
And now we're going to go for lighting with the shaders. So basically what we're doing is we're going to calculate lighting during its lighting pass, and it'll grab a sample texture from the components from the frame buffer from the geometry pass. And this will allow us to get our normal, diffuse, and specular values. Using those values, we're able to calculate the blend Phong lighting, and it's basically Phong lighting with a half direction. The diffuse will shine on all directions. It's what allows us to have a color on the object. Specular is a reflection off the object at a certain angle to the normal. Attenuation is how far the light travels. So as Stephen mentioned before, it's pretty high in ours so that we can see everything. and ambient itself is just, I guess, natural lighting, so that we're able to see in any dark areas, but not able to since our attenuation is pretty high at this point.
Okay, so now I'm going to talk about our color correction. So in a deferred rendering system, to do color correction, you would create another frame buffer. So after you've done your geometry path and your lighting path, you create another frame buffer after your compilation to do any post-processing effects. What we did in our code is actually added to our light path at the moment, so it's not technically deferred at the moment because we semi-running out of time for it. But basically, we're using a lookup table to display a warm color field to our scene. So we take our scale of our actual LUT, we offset it by the LUT table. So a LUT table is basically a lookup, like it's a table of values that give you different color information, and what we do is sample from that color information in a 3D texture and apply it to our total light calculations. So if you see in scene here in our nice little game, you see the warm color field we have for everything? Yeah, that's all applied with the lookup table. And yeah, so the lookup table is here, and we apply it right down here to our lighting.
All right, going on to movement. In our movement, we're actually using GLSW, and we're using a callback per frame from any information that the keyboard gives. It updates a global variable, and that will update the object mesh. And what we have it set as is to multiply delta time by 20, and this will allow a consistent speed for us to move. Actually, if he loads it, you should see the fisherman able to move left and right. It didn't really make sense for vertical movement at this point. And you can see the two fish at the bottom. One is using a sine function, the other is using a cos function to update its translation. And we're using the current frame time as input values and multiplying by 4 and -4 to amplify the movement so that it's an acceptable variance for random, just for movement's sake.
Okay, so we're just going to go on to the blurring effect. We didn't actually apply blur to our actual object here, but I'm going to go through a shader code to actually how you can actually implement a blur function. Specifically, well, it's technically a Gaussian blur, sort of, kind of, not really. But it basically, when you're doing a blur, you're taking a texture value of your actual screen. You're going to offset that value, as you've seen in our shader code, by different values. So we set our offsets to different corners of our actual screen. That's how we're going to blur it by a matrix. So basically, we get our screen texture. We multiply it by a kernel, which is the different matrix of different values that allow for pixels around a certain object to be offset or changed. So basically, when you have something on screen, you'll have like 1, 1, 0, 0, 1, 1, depending on where pixels are drawn or not drawn. This allows us to offset some of them to different values that gives us an actual blur effect. So basically, in this shader, we set our offset values, we set our kernel, and we sample from these kernels to get our actual blur on screen. And that's how we would apply blur. And when you do that, you will get, I'm going to show you an example from learnopengl.com, an actual blur. I could bring this up quickly. Well, I'm going to show you Bloom. So Bloom has a blur. So basically here you could get a blur like this. This is just in the Bloom tutorial because Bloom uses a blur pass to actually get the values it needs. But you could blur your screen like this. And I think that's about it.
Yep, that's all.
Okay, thank you guys for your
All
time.
right, thank you very much.